The Maclaurin series and the radius of convergence for f of z equals e to the minus z squared, and f of z equals z times the cosine of pi z. So for the first one, we'll start with e to the z. That has a Maclaurin series that converges everywhere. Z to the k over k factorial. Therefore, e to the minus z squared will have a Maclaurin series, which just means a Taylor series centered at 0. So the center z minus z0 to the k, when the center is 0, then we just get z to the k, which we have here. So e to the minus z squared, we have minus z squared to the k, just replacing this z with minus z squared, divided by k factorial. And now simplifying, negative 1 to the k, and then z squared to the k is z to the 2k. So there's the Maclaurin series for e to the minus z squared, and this series will converge for all z. So the radius of convergence is infinite, and that comes from the ratio test. And we'll see that one in detail when we do number 2 here. It's basically the same. So f of z equals z times the cosine of pi z. So first we'll start with cosine of z. Cosine is an even function, so we get the even powers. It's negative 1 to the k, it alternates, and then it's z to the 2k divided by 2k quantity factorial. So this is cosine z. We'll do this in 2 steps now. First we'll substitute pi z for z, and then at the end we'll multiply by z. So cosine of pi z, just put pi z in here, negative 1 to the k still, and then we have pi z to the 2k divided by 2k quantity factorial. And let's extract the coefficient here. Negative 1 to the k, pi to the 2k, z to the 2k, divided by 2k quantity factorial. So that's cosine pi z. We want z times cosine pi z, so f of z, which is z times cosine of pi z. We just have to multiply this whole thing by z, which is going to raise the power on z here by 1. So we can just write the answer. It's everything we see here, but instead of 2k, it's going to become 2k plus 1, because we're multiplying by z. Negative 1 to the k, pi to the 2k, z to the 2k plus 1, divided by 2k factorial. Now for the radius of convergence, the ratio test will be nice here. So we will see that this converges for all z by the ratio test. We'll look at the limit as k goes to infinity of ck plus 1 divided by ck in modulus. So the limit k goes to, and this limit is going to be 0 for any z, which means the series will converge for any z. So we have the limit as k goes to infinity. The modulus of ck plus 1, the modulus of negative 1 to the k is 1, so I'll ignore that. We have pi to the 2k, modulus of z to the 2k plus 1, divided by 2k plus 2 factorial. Sorry, so this should be, I'm replacing k with k plus 1. So this should be 2k plus 2 here, and this should be 2k plus 3 here. So 2k plus 2 and 2k plus 3, because k should be replaced by k plus 1, which means 2k is replaced by 2k plus 2, and 2k plus 1 then is 2k plus 3. and then times the reciprocal of this, the modulus, is 2k quantity factorial. The modulus of that is 1, so we'll skip it. Pi to the 2k, z to the modulus of z to the 2k plus 1. And now this is equal to, simplify things, pi to the 2k plus 2 divided by pi to the 2k is pi squared. And then the modulus of z squared, and then divided by 2k plus 2 times 2k plus 1. Z is considered a constant in this limit because k is going to infinity. So the denominator goes to infinity, the numerator is a constant. We have a constant over infinity, which is 0, and so therefore the radius of convergence is infinity. So it converges for all z.